The broadcast is now starting. All attendees are in listen-only mode.
Great. Well, welcome, everyone. My name is Johnny Bass. I'm here to talk a little bit about what's going on with the migration from IPv4 to IPv6. Who am I? Well, I've been around in the industry for a while now. I've been doing computer networking, as it says here, from the late 80s. So I've got a lot of time in. I've been dealing with Cisco equipment specifically now for 24 years, I guess. So again, I date back quite a ways in networking and specifically in the Cisco environment. I have worked and I still do consulting work within the provider space and enterprise as well. I'm a CCIE. I have been for a while. I teach a lot about CCIE types of content. I'm a CCSI, which just basically means that I'm a Cisco certified instructor, so certified Cisco systems instructor. And again, I teach a lot of route switch types of courses specifically for global knowledge, and I'm the course director for several different programs, including the service provider track of classes within global knowledge for North America, the CCIE program for route switch for North America, and I'm also the course director for IPv6 for North America. So I do a lot of classes, and I also do a lot of consulting work. I've helped out in several different significant implementations of IPv6, so we'll probably interject a little bit of that as we go along. Live in Gig Harbor, Washington, which most people don't know where that is, so that's the Seattle area. It's technically closer to Tacoma, but again, it's just easier to describe. And as you can see there, I try to spend as much time with the family as I can and do family types of things, but every once in a while I try to get a little bit of golf in, a little bit of scuba diving, or other things. You can follow me on Twitter, or you can connect up to me on LinkedIn. Also, feel free to drop me an email. My email account is up there at the top, and eventually I'll get back to you. I do get about 200, 300, 400 emails a day, so if I don't get back to you right away, then it's not anything personal. It just means that I've gotten a lot of emails. And if I haven't gotten back to you after a couple days, probably resend it, because I do get a little heavy-handed at times with the delete key, so again, it wasn't anything personal. So to talk about IPv6, we have to talk a bit about where we came from or what we're moving away from. And so really, looking at IPv4 first makes a lot of sense. So IPv4 has been around for a while now. RC791 is the one that defined IP in general, and it's the first IP specification. So request for comment came out in 1981. So it's been around for quite a while. The whole rationale behind it was to be able to support the DARPA project. And so DARPA was an interconnection between defense contractors, the Department of Defense, universities, and we needed something to be able to give us the ability to be able to communicate from one location to the other. So we needed some type of networking addressing that was an open specification. So we already had something, or several somethings out there that were vendor specific, and we were looking for something that was more generic. So IP was that protocol that was going to fill that bigger need. There's others that were trying to come up with solutions at the same time. They saw similar types of needs, but RC791 came out first. That's the one that we basically adopted and we kind of moved forward with. The Internet basically evolved from this DARPA project, and the Defense Department realized fairly quickly that they were losing control. I mean, basically, it came down to UCLA was the first one that really kind of started adding more and more devices onto the network, more than what was expected to be there. And the Defense Department realized fairly quickly that, yeah, they're going to lose control. But the usability of this interconnection, all these networks that were interconnected worldwide, wasn't exactly, it wasn't very usable. It wasn't very user-friendly. And so you give a problem, you give a need to a bunch of physicists, and they'll come up with some type of solution. And so some physicists at CERN, which is a particle physics lab out of Switzerland, France, they are the ones that came up with this this concept of a GUI interface for networking. And so they're the ones that basically came up with the concept of the web. It took a little bit of time for it to catch on, but it definitely caught on in a big way, and it completely kind of blew IPv4 out of the water. We had some significant issues with it early on, because if you go back to RC 791 and you start looking at how they defined how IPv4 is supposed to be used, we really are not using it in that way any longer. And it didn't take very long for us to kind of figure out that there was a problem there. As you can see here, once we really started doing web type of behavior, the need for addressing really started to explode, and we started running into some significant problems. We realized in the early 90s that, yeah, this addressing scheme is not going to survive. So we started looking at some possibilities, and there were some proposals that were presented through RC form, looking for replacement for IP. So what can we do to be able to replace IP? There's some pushback that happened as far as trying to come up with replacements. Apple, for instance, basically produced their own RC, saying that there was really no need to replace IP, we just need to be better at how we manage it. It was a little short-sighted, and luckily nobody really kind of paid attention to their RC. We started looking at other alternatives. One of the things that we kind of realized fairly quickly, though, even if we came up with another addressing scheme, which we have our first proposal for IP Next Generation, that came out in 1993, that we need some time to be able to develop the services to be able to support whatever the new protocol happens to look like. So at this point in the IPv4 world, we were already starting to develop things to make it more user-friendly. We had ways of being able to do name lookups so that people didn't have to memorize numbers to be able to get to these different websites. So initially it depended on whether or not you were on the Unix side or a PC side of the house as to how you did this. Eventually we all kind of standardized on DNS to be able to do lookups. We also figured out that doing static addressing wasn't exactly very attractive, and so by this point we were also coming up with solutions on how to be able to allocate address space for the v4 addressing to the client. So DHCP, Dynamic Host Configuration Protocol, was developed. And so these different services really didn't exist yet for any other protocols, because we're still trying to figure out what that really is going to look like. IP Next Generation is IPv6, and so it was basically the initial RCs for proposing the concept of v6, and from that point forward we started to develop more and more standards. And so the real v6, kind of what we're basing everything off of today for IPv6, came out of RC 1883 in 1995. So again, 94-95 time frame, we were concerned with the amount of address space that we had left already for IPv4, and we had a solution with IPv6, but we didn't have the services. So we needed something as a band-aid to be able to extend the lifespan of IPv4. And the most significant lifespan extension, the most significant band-aid, for no better term, is RC 1918. So RC 1918 gives us private address space. So we had this proposal asking for, or proposing the idea of having private address space, but RC 1918 actually defines what that means. And so this is where we get the 10 address space and the 172.16 through 31 and 192.168 address space, the entire block of Class C. So we have a Class A, a Class B, and a Class C being set aside just for the purpose of using IPv4 internally and not to be used on the internet. So those address spaces are considered to be off limits for the internet. They're considered to be Martians, or they're part of the Bogon list. They're not supposed to exist. They're not supposed to be advertised to the internet. To be able to use IPv4 though with private address space, and you still want to communicate to the internet, we needed to also have translation. And so we, at the same time frame, we had IPNAT so network address translation, that allows us to be able to translate from one v4 address to another v4 address. Today we use the terminology NAT64 for the concept of translating from an IPv4 address to another IPv4 address. We had to get smarter in the way that we're using v4. Again, if we go back to RC 791 and we look at how they recommend to use the address space, they never had this concept that this was going to be really this global internetwork. They never really thought that there was going to be this number of devices, this number of networks that are going to be attached together to make this overall global infrastructure. And so they basically defined three types of networks: small, medium, or large. Small networks for Class C, 254 hosts apiece. A medium-sized network was going to be a Class B, 65,000 possible hosts per Class B network, and then large networks were going to be Class A with 16,777,214 possible hosts. Okay, so really large networks. There was no concept of subnetting. So their idea here was that you would be able to use a whole Class B or Class A on a single network and have as many hosts as you possibly could ever want on those networks. What we realized very quickly was that wasn't going to work. When I first started really kind of doing networking in a big way, and when I really first started playing around with Cisco gear back in 1990, I went to work for a large aerospace company based in the Seattle area, and we had roughly 45,000 devices all within a single broadcast domain, all using a single Class B, trying to get up to that 65,000 number, and we were having problems every day. I mean, it just wasn't stable. The amount of overhead traffic was just extreme, and it just didn't work. So those concepts were interesting, but they just weren't really usable. So we had to get smarter about it. And one of the things we started looking at is how do we break these network up into something a little bit more usable. So subnetting, borrowing, which I don't really care for the term borrowing because it's like your kid's borrowing money from you, they're never going to give it back. So it's repurposing. And so repurposing some of the bits that were host bits to become more networking bits. And so we get more networks out of them, but the networks just happen to be smaller. And that makes a whole lot of sense, especially when you start talking about the bigger type of networks like Class B and Class A. And that doesn't mean that you can't subnet a Class C, and you definitely can. But we needed to be able to get better utilization out of the address space that we had available to us for both Class B and Class A. The ability to be able to advertise the mask that goes along with the subnetting. The ability to be able to adjust the mask depending on the need of the link. So how many hosts do you have on a given segment? So variable length subnet masking. CIDR, classless interdomain routing, was the ability to basically be able to advertise the network however you needed to. So the routing process having the capability of advertising it with either a classful mask or a subnet mask, or combining classful networks together to reduce the amount of information that you're advertising. So summarization or aggregation, all this stuff is basically falls underneath this umbrella of CIDR. And again, just trying to be smarter in the way that we're doing things. IANA, which is the global authority for names and numbers, they allocate address space to the regional registries like ARIN here in North America, and RIPE in Europe, and the Asia Pacific NIC, and the African NIC, and the Latin American NIC. They allocate address space. They started getting a little bit smarter about how to allocate that address space. Because initially they were allocating whole Class A's. But again, who they were allocating that address space to may or may not use all that address space. So they started getting smarter about that, and they started to register and allocate and allow for the regional registries to allocate subnets. And so you'll see if you go up to IANA.org, or if you go to ARIN.org and you start looking at the way that they're allocating address space, you'll see that there's subnets in there. So subnets of different Class A's. Just trying to get better about it. This internet thing is not getting any smaller. So the last time I checked, which was a few days ago, and we had 215 million, actually it's about a month ago, 215 million different domains that are registered. And these are the major top-level domain names, so .com, .net, .org. There's a lot of other dots that are out there that aren't included in this count. So I just if you Google it, you'll find that there's statistics that you can pull down as far as the number of domains that exist on the internet, and 215 million. Currently, we have 2.4 billion people that use the internet. How many people do we have on the planet? Well, okay, last time I checked, it was just short of 7.2 billion people on the planet. So we have growth potential there. That's a bit of a concern for us as far as IP addressing is concerned. So we need additional address space. It just was never, v4 was never really designed to be used in the way that we're using it today. So IPv6 is the replacement. Now there's alternatives. We looked at other possibilities in the past. We looked at something like OSI, for instance. So the Open System Interconnect is a protocol that was developed by the ISO group out of Europe as a potential replacement for IPv4. Never really kind of took off. I mean, there's some that used it and others that looked at that and go, that's a little bit more complicated than we would like. It had a much larger address space to be able to handle the need that everybody kind of already foresaw for the internet and beyond. But again, it was overly complicated type of protocol. It was completely replacing IP and everything that was running on top of IP, and so all the applications would have to change and everything like that. And so that was it was more than what we really were willing to do. IPv6 looked like a much better candidate for replacement because it's still considered to be IP, even though the address space looks different. We'll look at a comparison here in a minute between v4 and v6, and v4 being 32-bit addressing and v6 being 128-bit addressing. The representation of the addressing is going to be different, but what rides on top of it doesn't really have to change a whole lot. The applications that know about layer 3 had to change, but the applications that don't, in which case most applications don't have really visibility at layer 3, there's no change that was necessary. Those applications run on top of either TCP or UDP. TCP or UDP still run on top of IP. It doesn't matter if it's v4 or v6, it still runs on top of IP. So great. v6 is an easier transition than some other protocol that would have been used to replace IPv4. So why do we need it? Well, okay, the party line is that we have no more v4 address space to go around. And we still have lots of people out there that aren't on the internet yet, that want to be on the internet, and there's more and more things that need addressing. Okay, so we have some issues coming up. Now, are we really out of v4 address space? Okay, relatively speaking, yes, but no. Okay, so kind of. There's no more address space from IANA to allocate to the regional registries. So again, IANA is the global authority for names and numbers. They're the ones that basically manage IP, both v4 and v6 for the planet. They're the ones that manage the protocol identifiers or port numbers that ride on top of IP, v4 and v6, and on top of TCP and UDP. They're also the ones that manage the top-level domains. So they're the ones that create the new dot whatevers, so .tv or dot whatever. And so they're the ones that basically have to deal with all that, and then they delegate the responsibility of downstream to others, to regional registries, to local registries, for both address space and also for domain name registration. So they're not in the business of doing that. But IANA basically ran out of v4 address space to be able to allocate to the regional registries. So there's the list of the regional registries. So the African NIC, the Asia Pacific NIC, ARIN, again North America, Latin American NIC, and RIPE, which is for Europe. Now, the reality is that there was a milestone that was predefined by IANA and other organizations around the world that once they got to a certain level of address space left, they would dump the last of it to Africa. And so the African NIC, that's why you can see that they have the largest amount of address space left of, as far as percentages are concerned, is because on February 3rd, 2011, they hit that milestone. So IANA basically only allocated address space in increments of /8 blocks, so basically the equivalent of a Class A, but they were combinations of Class Bs or blocks of Class Cs that they're allocating. And once they hit that particular milestone, then they dumped all what was left to Africa. So Africa still has a significant amount of their address space left. But looking at the rest, you can see the Asia Pacific NIC is below 2%. ARIN, North America, we're down to 1%. And this was as of yesterday. So I looked yesterday, and what's interesting is the Asia Pacific NIC and RIPE both, their numbers have actually increased a little bit over the last couple months. So the Asia was actually down to about almost 1.5%, and they've gotten 0.2% of their address space back. RIPE was down to about 1.8, and so they got about the same amount back as well. Now, what they're doing though is they're not going to, well, they're being really stingy at allocating their address space. So the major players here are really kind of trying to not allocate any more v4 address space, but trying to push out the v6 stuff. And what's happening then is, as v6 is starting to roll out, some of the v4 address space is basically going back into the pool. And so they're freeing up some of the v4 address space by starting to implement v6. The v4 address space that goes back in the pool does not really become available to reallocate. And so they're holding on to this just in case they need it. And so the numbers for Asia and RIPE in particular have been really kind of holding steady for a while now. And again, they started to increase just a little bit, but they haven't really been decreasing because they've really been forcing most of their customers downstream to move towards v6, because again, that just makes sense. Here in North America, we've really been the slowest at implementing v6. The rest of the world has really had no choice in the matter. Europe and Asia both have been at a fairly small number of percentage for a significant amount of time now. And ARIN has had more of their address space, and we've just been putting v6 off for a while. So it wasn't until we actually hit that February 3rd milestone date that it really kind of woke us up a bit and started really kind of pushing us forward. Plus mandates out of like the U.S. federal government and other governments worldwide that are trying to push us forward into the v6 world. So great. Lots of people out there, but not enough addressing. Yeah, well, this whole DARPA project thing started in the U.S., started with the Department of Defense, the U.S. Department of Defense, and defense contractors and universities within the United States. So it kind of makes sense that we have, as the U.S. has the most amount of address space. So out of all of the possible IPv4 address space, 60% of it is allocated to the U.S. A lot of that address space was allocated to the U.S. before IANA existed. And so back in the day, when it was the DARPA project, any of the defense contractors, any of the universities basically could get address space and get as much address space as they wanted. Even once the government started realizing that this is no longer going to be really valid for its original project, for its original intent, the U.S. still got more address space than everybody else. All this address space was considered to be pre-IANA, and that address space is considered to be yours. So as a company, if you were around back then, and there are some companies like Boeing and others that were around and involved within those projects back in the day, that address space is considered to belong to them. It's pre-IANA, and I mean, like Nortel, for instance, put a Class A on their assets sheet because it was pre-IANA. They claimed it to be theirs, and they claimed it to be to have some value. So a lot of address space has been allocated to the U.S. That doesn't leave a lot for the rest of the planet. So they really haven't had a whole lot of choice. You know, it's pretty significant. You know, you look at the number of people that we have in the U.S. compared to the rest of the planet, and the amount of address space. We have a lot of address space. But again, we're down to 1% as far as ARIN's concerned. There's still a lot of address space out there. You know, if push come to shove, I mean, we really have a lot of address space. There's a lot of address space that's being used internally that's not being used on the internet that we could start auditing and start going back through if we really had to. But we don't want to. We want to move forward with IPv6. Again, there's more and more need for address space. So not only do we have this need for the number of people that want to gain access to the internet, I mean, that by itself is a huge number. So I mean, theoretically, not all 7.2 billion people are going to want access to the internet, but okay, 5 billion, 6 billion people are going to have access. And so more and more people are going to want to have access to the internet. That's a huge number, but more and more things need address space. Since 3G cell phones, the cell phones have been operating on top of IP. And so 3G and 4G cell phones basically use IP address space to be able to do things more than just be able to have your smartphone and be able to surf or to be able to check your email, but it actually basically does VoIP. And so you're essentially doing voice over IP on the cell phone. So that means that every cell phone needs to have address space, needs to have some kind of address space to be able to write on top of. Okay, that's a big deal. You look at big providers out there, and they need a tremendous amount of address space. Now, they can get away with private address space for a while and then do translation, but that only works for up to a certain point. So we need a lot of address space. Cable TV, more and more cable providers, everything's running on top of IP. If nothing else, I mean, your cable boxes, your set-top boxes themselves are typically managed using IP. So even if they're not carrying the video traffic itself over IP, which more and more providers are doing today, but even if they're not doing that yet, the set-top boxes themselves are being managed through IP. So I know of one pretty major cable provider. They've gone through the 10 space more than once, and so they're having to NAT internally because of the number of cable boxes that they have out there to be able to manage those devices. Again, V6 is a great candidate for stuff like this because V6 is such a huge address space. I mean, cell phones, no problem. Cable boxes, especially for I mean, applications where the end users don't see the addressing. So as an end user of a smartphone, I don't really care what my address is. I don't care if it's a V4 address or a V6 address. The only thing I care is that I can make a phone call and that I can check my email and I can jump onto my social media or whatever. So I want to be able to do whatever it is I want to do, and I don't really care what the address space is going to be. More and more appliances have intelligence to them so that we can monitor their state, and some of them have like refrigerators you can buy with basically a PC that's built in, so you can build your grocery list or whatever. There are different car manufacturers out there that are basically trying to add intelligence to the cars to be able to report back to your dealership when you have issue with your cars, so for maintenance, for support. Obviously, there's a little bit of concern about, tracking driving habits and things like that. Maybe a little bit of Big Brother going on there, but basically, this is starting to happen today. There's a couple manufacturers out of Germany that are basically doing IP-based solutions within their cars to be able to report back to the dealership, so that when it's time for an oil change or a tune-up or whatever, then the car reports back to the dealership then gives you a call to let you know as a customer of theirs that it's time for you to bring the car in for service. At the Consumer Electronics Show this year, there were some toothbrushes that were basically introduced that were intelligent toothbrushes that would allow you then to be able to track their use and to see how your kids are brushing their teeth. So there's more and more things. I mean, we used to joke about this in the past. Oh yeah, everything's going to need address, including toothbrushes, and sure enough, somebody's come up with an application where a toothbrush actually needs to be addressed. We're starting to hear more and more of the terms of the Internet of Things or the Internet of Everything. The Internet of Things is more of a generic term that you hear used out there. Internet of Everything is more of a Cisco term, but it basically means the same thing. We're going to have a lot of stuff out there that's going to need addressing that's going to be managed. We hear the term cloud a lot nowadays, and so cloud management of devices. Things that could be at your home, things at work that are basically, that don't have necessarily a user interface, but that need to be somehow managed. So I mean, think about like a smart home. You could do everything IP-based, so that you can manage your lighting, your temperature, your sprinkler systems, whatever. So everything could be IP-based, and so everything, all this stuff needs address space. This is, a huge potential market in the future, and also a huge consumer of address space. The other thing that's kind of attractive about IPv6 is the embedded security. So one of the things that they realized very early on is that as addressing started being used for public purpose, things going across the public infrastructure, unfortunately there's people out there that want to either be disruptive, that want to steal stuff, that, you know, we need security. We need network security. And so in the development of IPv6, they decided, they as in the authors of the different RFCs for IPv6, decided that, okay, security is such a big deal that they're going to go ahead and embed security into the protocol itself. So rather than adding security on top of the protocol like we did with IPv4, it's considered to be native to the protocol. Technically, the security that we do for IPv4, so if you look at IPsec, IP security, it's an add-on protocol or a set of protocols that ride on top of IPv4. That stuff was developed for IPv6. So the reality is, if you already know IPsec for IPv4, you already know IPsec then for IPv6. The algorithms that we use for security for v6 are identical to what we do for v4. The way that we implement it is slightly different. The way that it's carried within the stack is different. So with v4, security is carried above the v4 protocol. With v6, it's considered to be extensions. So again, considered to be natively part of v6. There's some advantages of v6, even though the address space is so much larger. 120-bit addressing versus 32-bit addressing. The processing of the packets through a router is more simplistic. v6 is easier on the network than v4 is. And okay, you know, there's some basic stuff here. What they've done is in the v6 header, they've removed some of the fields, or not necessarily moved, but they've moved some of the fields that aren't necessarily used very frequently out of the base header. So in IPv4, we have certain fields that are always there, even if we never use them. So things like fragmentation, for instance. And so if you're going to be doing fragmentation, then okay, great, you need to know where this fragment fits within the reassembly process. Is it at the beginning, at the end? So we need to know what the offset is. We have to have an identifier for the fragment. We have flags to go along with it, again, to indicate where we are within that. But we don't always fragment. So why have those fields? So for IPv6, we do have the ability to do fragmentation, but if we're not going to, then don't have those fields. And so if you look at the base header for IPv6, those fields don't exist in the base header. Instead, fragmentation is handled by an extension. And so IPv6 uses header extensions to be able to add additional functionality. So one of the functionalities that can be added is going to be fragmentation. But one of the things that's interesting about fragmentation when you compare v4 and v6, any device in the path can do fragmentation unless a flag is set within the IPv4 header that says do not fragment. And so that means that a router or a firewall somewhere in the path between the original source device and the final destination could decide that this thing's not going to fit out the egress interface, and so I need to do fragmentation. Well, with v6, that's not going to be the case. And so with v6, if the packet comes along and hits a router or a firewall, and it won't fit out the egress interface because the master transmission unit is smaller than what you're trying to shove out that interface, then the router or the firewall is not going to do the fragmentation. Instead, the router or the firewall are basically going to end up dropping that packet and then send an error message back to the original sender and tell the sender that it didn't fit. And so we send back an error message, an ICMP error message that says packet too big, and that ICMP message carries what the MTU size is of the egress interface, so it's up to then the sender to do either fragmentation or to reduce the payload so that it will fit out that egress interface. So though it's one of the processes that's now been kind of offloaded from the routers, they don't have to do this any longer. So the only time the router is going to do fragmentation or a firewall is going to do fragmentation is if it is the source of the original payload. If it's not the source, then it doesn't do it. The other thing that we've lost in the v6 header compared to v4. In v4, we have a error checking. And so we have a CRC, a cyclic redundancy check. It's to check to make sure that the thing hasn't been corrupted. But the reality is we typically have it at layer 2. We have it at layer 4. So with IPv6, they kind of determine there's really not a need for it. There's no need for doing this error checking at layer 3. We already have it at layer 2. We already have it at layer 4. So it's going to be picked up at some point. So why do it again at layer 3? Now, at first glance, I mean, even when I was looking at this, it's like, you know, that doesn't sound like that big a deal. So why are they making it sound like a big deal? Because it turns out that it really is. Calculating that CRC is not that bad, but we have to recalculate it anytime that there's a change. Well, if we think about how packets flow through a router or through a firewall, as we go through those boxes and we're routing that traffic, we have to decrement the time to live. Okay, in v6 that's called the hop count, but in v4 it's called the time to live. It's looked at exactly the same way. It's interpreted the exact same way. And we have to decrement that value, which means that we've made a change then to that header. With v4, that means then that we have to recalculate the CRC because we've decremented the time to live. That happens through every single router. Now think about the internet and the number of routers that we have on the internet and the number of packets then that we have to send across the internet. Okay, and so we're into exabytes worth of data that's passing through the internet today, and so all those things have to be recalculated because we're decrementing time to live. And so we're trying to do some shortcuts out there, and we're trying to get around that in where we can. But I mean, still, there's a lot of CPU cycles within the routers having to be spent to be able to recalculate just because we're decrementing the time to live. So in IPv6, we don't do that. In IPv6, we're going to decrement the hop count, but because there's no CRC within the header for the IPv6 header, there's not going to be any CPU cycles spent recalculating that value. So again, initially that sounded like, well, that's not such a big deal until you really start thinking about the scope of the internet and how much traffic is actually flowing, and therefore how much processing is being spent to be able to recalculate that little value. So a quick comparison between them, yeah, much bigger address space. 4 times the size. Now, it's not 4 times the number of addresses, it's 4 times the number of bits. And remember that every time you add a bit, you double the possible combinations. So with 32 bits, we have 4.29 billion combinations. With 33 bits, we're now talking about 8.5 billion. Okay, so every time we add another bit, it's going to double the possibilities. Now, ignore the fact that I just said that there's 4.29 billion for 32 bits. Got to remember that with addressing, there's certain combinations that we can't use. You know, so when you're looking at what is available for unicast communication, so from host to host type of communication, with IPv4 we're talking about somewhere in the 3 billion range. I mean, it's still a lot of address space, but that's assuming that you're not doing any subnetting. That's just taking the class A, B's, and C's and combining all the possibilities together. Once you start breaking those things up into subnets, you're going to start to lose more and more address space because of the way that we do things within IPv4. With IPv6, again, we have some things that are off limits, so you're not going to be able to use 2 to the 128 possible addressing, but it's still a huge number. And so technically for the internet, we have 2 to the 125th possible combinations of addressing. Again, we're not going to use that many addressing, and there's some combinations that are off limits. We have a subnet mask to go with IPv4 to tell me which bits are going to be used for networking, which bits are going to be used for hosts. We have classful networking and we have classless networking with IPv4. There's no such concept in IPv6 because there is no classful networks in v6. So instead of calling it a subnet, we just basically, we have our prefix, and the prefix is going to be defined by a length. The length tells me how many bits are going to be prefixed, which are basically the equivalent of the network bits from IPv4. Whatever is remaining then are going to be host bits. Now the mask in v4 can be represented in dotted decimal or as a length. In v6 it's only represented as a length. So we'll see /64, /32, /whatever is on the v4 side. Again, it's been much more common lately to be able to use like /24s or /16s, but we normally have to configure things in dotted decimal, but when we display it, it'll be shown as a length. We use ARP, Address Resolution Protocol, to be able to resolve from layer 3 to layer 2. In IPv6, there's no ARP. There's no broadcast in IPv6, and so we'll get to that here in a second. So instead we use neighbor discovery. It's using an IPv6 message to be able to do neighbor solicitation, and then we get a neighbor advertisement back to be able to resolve layer 3, layer 2. Which does mean then that we have need for additional addressing to be able to source some of this stuff, because again, we use ICMP a lot in v6, more so than we do in v4, to replace some of the older applications or add-on protocols. Again, no broadcast. We have multicast instead. Broadcast tends to be inefficient. Non-IPv4 devices may pay attention to the broadcast messages because they come out as layer 2 broadcast. So we don't have broadcast in v6. It's only going to be done in multicast or unicast or something called an anycast, which we'll get to as well. Again, fragmentations are not done by routers anymore unless they're the source. They're done by the original hosts. So again, that's pretty good reduction in processing on the routers. Security, again, was an add-on. Security is considered to be native for IPv6. The minimum transmission unit for the protocols, these are defined by RSC. This is in case the applications that are running on top of either v4 or v6 have no visibility down to what the MTU size is at layer 2. There's a minimum assumed MTU size. So for IPv4, the minimum assumed MTU is 576 bytes. Now, a lot of applications assume bigger than that, but again, this is based off of RC 791, saying that if you really don't know, then assume it to be 576, which is not exactly the most efficient, since most network types are a minimum of 1,500 bytes or bigger. For IPv6, it's 1,280 bytes. Again, they could make that a little bit larger as well, but again, it's still more efficient than what IPv4 does. Now, again, commonplace. It's common in the v4 world. You assume that you have a couple hundred hosts. You're going to assume a /24, but it can be a /28 or /27, /30s, whatever it happens to be. On the v6 side, currently the recommendation is on LAN segments to use a /64 everywhere. So we're not really setting the length to match what the needs of the link are. Instead, what we're doing is we're coming up with a value that just makes it easy to implement. So this is something that goes back to one of the original RSCs for IPv6, and again, it's just for ease of implementation. Eventually, we're going to have to migrate away from the /64s, but for now, it just makes things a little bit easier to be able to implement. It's a huge amount of address space. The /64 means that the first 64 bits are going to be prefix, and the last 64 bits then are going to be host. Well, to the 64 is this big honking number right here. So 18 quadrillion possible combinations. Based off of the fact that we have 7.2 billion people on the planet, that means that in one /64, every person that's currently alive on the planet could have 2.5 billion addresses. Okay, we're not going to use that much address space. But again, this is for ease of implementation. So things to be able to help us get v6 implemented. The thing that really kind of relies on the /64 is the stateless auto configuration. So stateless address auto configuration allows us to be able to make it easy for the clients, the workstations, the servers to be able to get address space dynamically. But it relies on the /64s. As we start to implement and transition to v6, we're not going to be able to natively have v6 everywhere. And so we're going to have to tunnel v6, and there's different options for tunneling. And so we'll take a look at how that's going to work, some different tunneling options. We have others that have come out with some different solutions to try to help us with first and last mile, and that's a big deal in the provider space. A lot of providers are getting their core up to snuff to be able to natively support IPv6 all the way up to their provider edge devices. They have native support for IPv6 to certain customers, the larger customers, but really it's the majority. So you think like residential, how are we going to get v6 to them? And so right now, that's a major hurdle for most of the providers, and so we're looking at different techniques on how to be able to solve that. That's the first and last mile to the customer from the provider. And different tunneling techniques, this 6RD thing, this 6 rapid deployment, was developed to help with that issue, with that first and last mile, as a short-term solution. And it's a very attractive solution. A lot of providers have jumped onto it. Again, alternatives to the stateless auto configuration for dynamic allocation of address space to clients, we have DHCP. And so if you're accustomed to DHCP for IPv4, it's very, very similar to what we're doing for v6. DNS has been modified because, again, we don't like to type in numbers. We'd rather type in a name. So we have DNS that's been modified to be able to support IPv6. If we have to, we can do translation. And we're going to have to do this for a short term. You're going to have devices out there that are going to be v6 only. We want to talk to v4 hosts. You're going to have those people that are going to be early adopters. You're going to have sites out there that are going to be early adopters that are going to transition from v4 to v6 and be v6 only. And you're going to have v4 clients that are going to be able to need to talk to them. So NAT protocol translation, NAT64, basically that's their point in life, is to be able to translate from IPv4 to v6 and back again. NAT66 to be able to translate from IPv6 to IPv6. So it's the equivalent of NAT44, so what we've been doing for a long time. Now, NAT44 was really developed for the intent of kind of band-aiding the fact that we're running out of v4 address space, so address depletion. NAT66 is not for the purpose of address depletion. And so the IETF, for instance, have been kind of pushing down NAT for quite a while and trying to keep it from being released, because they were kind of looking at it just from the point of view of address space. But the reality is that NAT is also used in a lot of organizations, a lot of corporate environments, as part of their security policy. So not advertising what the real address space is out to the outside world. And so really that's kind of the intent of NAT66, is to hide what the internal address space is that's being used from the outside world. So not using your real address space off to the internet, and that's really the intent of NAT66. The RC for this came out about 1.5 years ago, almost 2 years now. Cisco and other vendors are now starting to support it in a limited fashion, but they're starting to support it. Tunnels fall into a couple different categories. They're all overlay tunnels. So a tunnel is basically writing something inside of something else. So if you think about driving down the highway and you go through a tunnel, and so you're going through something else. You're going through a mountain. You're going through underneath a river or whatever it happens to be. So you're writing inside of something else to get you through an intermediate network. And so the idea here is that we could be writing IPv6 on top of IPv4 so that the intermediate devices don't have to have any awareness of v6. The tunnels can be done either manually or they can be done dynamically. The manual tunnels, we have generic routing encapsulation or just IPv6 inside of IPv4. So with the manual tunnels, you're defining the source and destination of the tunnels. They emulate a point-to-point type of circuit. And so you're burying the v6 stuff on top of something else that's basically writing on top of v4, or you're writing v6 directly on top of v4. So protocol identifier 41 is IPv6. That allows you to be able to carry v6 traffic directly, or v6 header directly on top of a v4 header. The dynamic tunnels, you define a source, but you don't define the destination. The tunnel interfaces then have to find out about the destination some other method. And so we either use static routes or we use neighbor statements within our routing processes to be able to define then where the destination is going to be. And so a single tunnel interface then can go to n number of possible destinations. And so a manual tunnel is point-to-point, a dynamic tunnel is point-to-multipoint. And what we have there are some different options. We have IPv4 compatible tunnels, which have basically been deprecated. We don't tend to use these, so don't see them very often any longer, because you didn't really put a v6 address into the tunnel interface. You basically would have a v4 address that kind of looks like a v6 address, but not really. The 6-to-4 tunnels were used heavily between different providers, especially in the early days of the 6-bone, which was basically the internet for IPv6. The 6-bone, by the way, has been deprecated since 2006. it was really a test bed to be able to see how to develop a worldwide infrastructure to be able to support IPv6. And we don't necessarily need the 6 mode anymore because theoretically the internet can support IPv6 natively, which we'll see is not entirely true, but we're getting much closer than that. Still see 6-to-4 tunnels in the provider space, typically between provider edge devices trying to hide v6 from parts of their network. You can also carry v6 over MPLS, and so a lot of providers are doing that as well. The ISATAP tunnels were originally developed to be able to support clients, so workstations would be able to create a tunnel between them and a router, and you would carry then the v6 traffic over v4. ISATAP can also be used between routers, and so you can do router-router using ISATAP as well. We see ISATAP more in the enterprise space rather than 6-to-4 tunnels, and 6-to-4 tunnels tend to be more a provider solution. ISATAP tends to be more of an enterprise type of solution. The Teredo tunnels, we are trying to get rid of these things as much as we can. You can see there I put in, it's been deprecated. Teredo tunnels were basically, again, a dynamic tunnel, and it was from client to a Teredo server someplace out there. And the main difference between it and the others was that the others would ride on top of v4. So I was carrying v6 directly on top of v4. Teredo carried v6 over UDP over v4. And its original intent was to be able to hide the v6 stuff going through a box that was doing NAT. And so part of the problem was those early devices didn't understand carrying v6 over v4, and so when we started doing NAT, it was confusing to those devices. So Teredo was created as a workaround. The problem today is that most people see Teredo as being a security risk because you are burying something on top of UDP, and depending on your firewalls, it may not go far enough into the packet inspection to be able to really see what the thing's carrying. And so a lot of people look at Teredo as being a security problem, and so we've been trying to deprecate it. Status auto configuration, again, trying to ease the implementation of v6. A client then will send out a solicitation to routers, and so it uses this router discovery to try to figure out if there's a router out there that supports IPv6. On a Cisco box, if you configure IPv6 addressing onto an interface and you configure IPv6 routing on that particular router, then it will automatically respond back to this router solicitation with a router advertisement. And the router then advertises what the prefix is that it's been assigned on that particular interface. And it advertises itself as the default gateway, and then there's some additional optional things that it can advertise as well, but not DNS or options or anything like that. It just it can advertise things like MTU size. It will advertise a lifetime, so how long this thing is going to be valid and preferred, but that's basically it. And we assume that the length is going to be a /64. Then what the client will do is it will take that prefix that it received, and again it assumes the /64, and then it will automatically calculate the last 64 bits. It'll either use a pre-configured, or it'll use EUI64, or it'll use, today there's options for privatizing the last 64 bits, in which case then it randomly generates the last 64 bits every time you boot up, and if you stay up for a period of time, it will recalculate that periodically. If you look at like the newer operating systems like Windows 8, that is the default characteristic. So it doesn't actually do the EUI64 process any longer. EUI64 is taking the MAC address and expanding it to be 64 bits long because it's only 48 bits by default. And it expands it by shoving in a shim of FFFE into the middle of it and then flipping it a bit to make it unique. The Cisco boxes, if you tell it to use EUI64, still does this process. The workstations by default today do not. You can disable the randomizing and the privatizing, in which case then it will use its MAC address as the base of the last 64 bits. Again, other things to help us out, the 6RD thing, again, is to help us with the first and last mile. This is an RC that came out of a service provider out of France, and it just makes a lot of sense, and it's very easy for the providers to implement this. It basically creates a tunnel, a 6RD tunnel between the client device and a 6RD relay device, which is typically just a router. It does a modified status auto configuration. So instead of getting a /64, what it gets is a /32. And so it assumes then it has to be a /32 from the provider. And then what the client device does is it takes its v4 address that it's using to communicate to the internet and embeds that as the next 32 bits of the IPv6 address. And so the first 32 bits is basically representing the provider. The next 32 bits is the v4 address of the client device, and then it randomly generates the last 64 bits, however it's set up to do it. A lot of providers jumped on board this 6RD thing very early on. It's a very popular solution. Long term, we're going to be using DHCP. And so DHCPv6 is available today. Different platforms support it, and slightly different implementation. So as far as the amount of support, it varies slightly from one to the other, but in general it looks very, very similar to DHCP that we're used to. We're using a multicast at layer 2, not a broadcast, because there's no broadcast in IPv6. So 3333 basically indicates a multicast relative to IPv6. It's going to be a multicast at layer 2, layer 3 as well. They've changed some of the terminology, but it basically does the same stuff. And so we do a four-way handshake, just like we do with DHCP for IPv4. So we're looking for servers. We get a server that's basically saying, hey, I'm here, I can support you. Then we can send out a request for an address, and then we get a reply with the address allocation. And then we have a lease that goes along with that, and so we have to periodically make sure that we're keeping that information current. Again, there's different operating systems that can support it as a server side, as a relay to be able to get us to the server, and then also on the client side. XP doesn't really support DHCPv6 very well. I've got a note on there about the third-party add-on, but Microsoft, basically their party line was that that XP does not support DHCPv6. So everything beyond XP does, and it becomes more and more complete as you go further along. DNS had to get modified because our address space has changed. And so we have quad A records now to represent the 128-bit addressing instead of just an A record. And so the DNS servers pretty much had to get modified, so by 9 or better will support v4 and v6. And when you request an address from the DNS server, the client can now include an address family. And so it can include whether or not it wants it as a v4 address or a v6 address or both. So whatever I have configured in there. One of the significant differences for v6 over v4 is whether or not we're going to automatically generate the reverse or not. And so the current draft recommends that we do not automatically generate the reverse for all of those quad A records. Now you can create your own pointers and put them into the DNS servers so that when somebody is doing a reverse lookup of something that's within your space, your routers, your servers, then it comes back with a fairly quick response. For those things that are not predefined with pointers, it still will be able to do the reverse. It's just that it has to do it dynamically every time that somebody types in a number to find the name. And so it's going to take a little bit longer for the response to come back, but it will end up responding. One of the issues that we have is the amount of memory, physical memory that we have within these servers, and be able to generate that size of a database. I mean, again, the number of bits for the address is 4 times the size, so it takes up 4 times as much memory compared to an IPv4 address. Again, we have different techniques for doing translation. If we're going from v4 to a v6 device or the other way around, we need something to translate. NAT/PT was the first attempt at this. Cisco iOS-based routers do NAT/PT. It has been deprecated. One of the issues with NAT/PT is that you had to set aside address space on both v4 and v6 to be able to handle this. But there's really no indication that there's been translation that's happened, so neither side really knows that there's been translation. One of the problems that we also had was DNS responses. Excuse me. And we have to worry about whether or not that address needs to be translated or not, and how to be able to handle that. So NAT64 basically takes over. NAT64 takes the v4 address and does embed it into the v6 address. Excuse me for a second. A little bit of a coughing fit there. So the v4 address is embedded within the v6. So there is an indication, there is a way to be able to derive that this thing has been translated. There's also hooks into DNS, and so there's a DNS64. So that way, if the device, the server out there is a v4 server, for instance, and a v6 host wants to get to it, then the DNS64 can do the translation of the v4 address to a v6 address with the v4 address embedded in it. And then when that traffic is heading in the direction of the device to a NAT64, it then recognizes that this has been translated and that the v4 address is embedded in there. And so you'll easily be able to translate this stuff back. NAT64 is more scalable than NATPT. It's definitely more reusable. Within the Cisco environment, right now, the ASAs can do NAT64, and the IO6R platforms can do NAT64. So eventually, we'll see the iOS XE devices be able to do it as well. Addressing within the v6 world, we have addressing for the planet. We have addressing that we can use internally. Now, again, initially the IETF didn't think there was a need for this, so we had site local defined in one of the original RSCs to use internally, and then the thought was that we would translate going off to the internet. The IETF didn't think that was necessary, so they deprecated the site local address space. But later on, we really kind of pushed through the need for NAT and as part of our security. So we had to have addressing then that we want to be able to translate from, so we can go to a global address space. So unique local is something that's been basically set aside to do that private address space. We have multicast. Again, we don't have broadcast. The entire planet right now is being allocated out of this 1/3. This is the global address space, so 2000 : so it's all in hex. We separate 16-bit blocks with a colon. The colon basically represents a boatload of zeros. So every time we look at v6 addressing, it's always 128 bits. So how much of it is going to be prefix, how much is going to be host. So as a shortcut, we can use in the colon. And so there's 128 bits there, but we were really only showing you 16 of it, and the rest of it's being represented by the colon. As I put in there, the /3 gives us 537 million /32s, which is a common thing that the regional registries allocate to the providers. So what you see being allocated to service providers out there are typically going to be these /32s. So we have a lot of them. If we ran out of this address space, there's more. So there's the 4,000 block, there's the 6,000 block, there's the 8,000 block that allows us to be able to do more and more address space for the internet. And as we do the Internet of Things, we're going to need more address space. Unique local, not runnable on the internet. Site local was also not legal on the internet. You can still configure site local even though it's not supposed to be used any longer. The systems don't know any better, so if you wanted to, you can configure site local. That's especially true for the early adopters that might have already been using it. Unique local is out of this FC00. Now, technically, it's two different blocks within that. So FC00:/8, the first half of it allegedly will be globally assigned. FD00:/8 is going to be what we use internally. I don't really foresee the FC00/8 ever really being used, but it's a possibility. In either case, it's not going to be advertised to the internet, and we're going to have to use translation like NATPT or NAT66 to be able to translate from this to a global address that's going to be used off to the internet. Multicast. Everything that starts off with FF is multicast. The next 4 bits indicates whether or not it's a permanent multicast or it's a temporary multicast. So if that 0 that follows the FF, if that's a 0 there, then that's a permanent multicast. If it's 1, then it's a temporary multicast. The next nibble, the next 4 bits, the next 0 that we see there is the scope. And so right now we only have the 5 different scopes that are available to us. Node local or interface local, which doesn't leave the box. Link local, which is not routable. So that's for local use between devices on the local segment. Site local, which is routable. So you would have to enable multicast routing for IPv6 for this to function, but site local and organizational local are not legal on the internet. So the only one that's legal on the internet is E. So FF0E, FF1E, those would be multicasts that are going to be used for the internet. Right now, what we're trying to do is we're trying to get to coexistence with v4 and v6. That's a short-term goal. So dual stack environments. So we'll hear the term dual stack or dual stack light or hybrid mode, where we're trying to do dual stack both v4 and v6 wherever possible. Where it's not possible, we'll do some tunnels to interconnect things. Back to Windows XP and beyond, we can support both v4 and v6. Since Vista, it will prefer v6 over v4 if we get it. So well, pretty much all the modern operating systems today will prefer v6 over v4 if it gets both. Again, the DNS servers have to be updated to be able to support the resolution to v6 addressing. And we're getting more and more of that. It is transparent to the end user. So a couple weeks ago, I was at Cisco Live, and they light up the entire conference with both IPv4 and IPv6. And as a client, you can't tell the difference. So you're going off to whatever website or your email or whatever. If it's possible that's carried on top of v6, it will do it. If not, then it will carry on top of v4. And as an end user, I couldn't tell the difference. The routers have no problem handling multiple protocols. And that's pretty much what made Cisco to begin with, was the fact that they had multi-protocol routing. Back then there was v4 as well as doing AppleTalk and IPX and things like that. So being able to handle IP and IP is really not that big a deal. The protocols don't interact. I mean, yeah, we can do translation and tunneling, but they don't technically interact, so they're considered to be ships in the night. Most of the routing protocols are independent of each other, so even though you have RIP and RIP, there are 2 different RIPs, one for IPv4 and RIP next generation for IPv6. OSPF v2, OSPF v3 for v4 and v6, and EIGRP, EIGRP v6. Now ISIs, you can run it as a single process, and it can support both, or you can tell it to separate it out. BGP is a single process that can support both. Again, it builds multiple tables though, so they don't really interact. Though you can carry v6 routes using a v4 relationship between the BGP peers or the other way around. There is some new development with OSPF version 3. We have some address families now for OSPF v3 that allows us to be able to carry both v6 and v4 routes across an OSPF v3 relationship. Again, MPLS can carry both v4 and v6, but the core MPLS network that basically makes up MPLS has to run v4. And so it cannot natively be only v6 yet. And that's because the label distribution protocol doesn't natively support IPv6 yet. It's still in work. The current draft version of the RC expires in August of this year, so hopefully that's going to get taken care of relatively soon. Again, we can have our translation to help have v4 and v6 coexist. So do we really have to have v6? Well, again, I mean, others out there, yeah, really do because of the address space. We have a lot of v4 address space. A lot of enterprises are looking at this going, yep, I don't need to do this right now, but you know, they're looking at it for long-term solutions. And so I've been dealing with a lot of enterprise looking at what their options are basically for long-term, because eventually we're going to get to a point where v4 is going to go away. And so there's either going to be mandates out there or just applications, devices that are only going to be supporting v6. They're not going to be supporting v4 any longer. So we will be forced to move forward. But we're getting better support now for v6. You can see that we've got 94% of the top-level domains support v6 as well as v4. The rest of it is catching up. We have 6 million different domains that can support IPv6 natively now. So, I mean, we still have a long ways to go, but we're getting there. We just got to keep moving forward with it. We're going to have to figure out how to handle the first and last mile as far as the providers are concerned. Within the enterprise environment, how do you want to handle it? How do you want to deploy it? Where do you want to deploy it first? And again, in a lot of cases, I'm seeing it where it's coming up in pockets within the enterprise network, and then tunneling between the different pockets just to be able to do testing of their applications. We have to figure out how we're going to handle translation, because you're going to have some v4 devices trying to speak to v6 and the other way around. So NAT-PT, NAT64. We have to figure out how we're going to do address plans for it, and then eventually we're going to realize that, okay, the /64 is not exactly the most efficient use of the address space, and so how we're going to renumber our entire v6 world to something a little bit more efficient. Now, luckily, this is things that's already been thought of. It's already within the RFCs. That's why there's embedded lifetimes within the v6 address space, just to make it easier to be able to renumber. And eventually, we're going to start turning things off as far as v4 is concerned. Talking with some of the providers, they don't want to support multiple protocols long term. It's not cost effective to them. I mean, initially we thought that as we start to roll out v6, it would replace the v4 traffic, but that's not really been the case. The v6 traffic has been in addition to the v4 traffic, because not everybody's really trusting of the v6 application, and so they're not willing to get rid of their v4 yet. So they're just kind of testing the v6. And so the providers are wanting to get rid of the v4 as soon as they can possibly do it. And so they're hoping that it's not too long term before we start shutting down some of this v4 stuff. Lots more information out there. I teach, and I'm the course director for the IPv6 course. We go into much more gory detail there, do lots of labs on it. We have some blog and white papers up on the Knowledge Center, the Global Knowledge, some of the stuff I've written, some stuff that other people have written up there. There's a lot of good information out there on v6, and the v6 forum has their site out there kind of keeping statistics as to how we're doing as far as our rollout of v6 is concerned. So hopefully this was worthwhile, and went a little bit longer than I had originally intended, but again, hopefully you get something out of this. Thank you.